Okay, so we talked about this idea of transverse and longitudinal waves. You're going to need those definitions here. So we can say that the wave can travel in two different ways. It can travel in the same direction or in the perpendicular direction of the direction of the wave. So if I have a slinky, listen again, I'm going to need you. Listen to that one. If I have this slinky, right, and I'm perturbing my slinky up and down, is it in the perpendicular or in the parallel direction to my wave? If I'm moving it up and down, it would be perpendicular because my wave is going towards Justin, but my hand is moving up and down. Let's just slow this down into nothing. All right. All right, now I'm going like this. The direction of the wave or the direction of the perturbation is going in the same direction or in the perpendicular direction of the wave. In the same direction. Okay, so that's the difference between a longitudinal and a transverse wave. Okay? This one's going to be perpendicular to the direction of motion, the direction of the wave rather. This is a perpendicular sign. Sorry. And this is parallel to the direction of the wave. Does that make sense? So you see here, the direction of the wave is always towards the right. This peak that I created is going towards the right. That's the direction of motion, or direction of the wave rather. We're good? See, the disturbance is perpendicular to the direction of the wave. Light waves and things like that are transverse waves. Sound waves are more longitudinal waves because the compression and decompression are high pressure, low pressure areas of air that create sound. Okay? So here we go. This would be a longitudinal wave, and you see this part here is compressed, then this part here is compressed, then this part here is compressed. So the direction of the wave is still going towards the right. The compressed part of the wave is always going towards the right. Okay, and sound is a an example of it. Okay? You guys know what a Rubens tube is? Anyone Google that before or YouTube that? It's pretty neat. A Rubens tube. You know what? We'll just do one in class. It has to do with fire. You guys will enjoy it. Okay, let's go. Um, we also talked about speed of a wave on a string or on a slinky or whatever, and we said that tension is important for this. And so that's what this equation is, and it's going to tell us that the velocity of the wave is going to depend on the force. I'm going to call this the tension force, or Ft, divided by this coefficient here. Now we're going to talk about this. This is the mass length density. Basically, is how heavy your wire or your slinky is per unit length. All right. Doesn't matter specifically what that is now because we're going to go into a lot of detail on this later on. This is just really just surface introduction. All you need to know though about this is that you can vary the velocity of the wave, right, by changing functions, changing things around. Okay. If I were to make my, if I were, according to this equation here, if I were to make my slinky, no, not my slinky. Let's say it was a string, a guitar string. Okay. If I had a longer guitar string, would that change my velocity? If I had my tension to stay the same, my mass per unit length to stay the same, but my length gets longer, does that change the velocity of the thing? William, you say no. Exactly, because length is not a variable in this, right? If you change the length, you're also increasing the mass of your string because you have more string, and therefore nothing changes, and your velocity along that string is going to stay the same. So your length of your guitar doesn't really matter. You have to be able to reach it, yeah. But it doesn't matter in terms of the velocity of the wave that you're going to be able to reach. Okay, moving on. Water waves are different. Water waves are a combination of both longitudinal and transverse waves. All right, so the water particles, not only do they move up and down, they also move left and right. In fact, they move in a circular way. Have you ever seen has anyone gone surfing? Yeah. Or have you seen like a movie or a show or a video clip of someone who's surfing? You can see, let me go back real quick. I have to turn off my auto rotate. Let's go back to this here. If you notice here, the wave isn't a perfect sine function. In this case, the wave is actually curling around. And this is a really strong wave. It doesn't follow like the sinusoidal typical wave that you might be used to. And that the reason for that is because the water particles are moving in a cyclical way, in a circular way. Okay? And this is what creates the way the look of the wave that makes it look like this, you know? It's a really bad drawing. You know, you get what I'm trying to say. All right. It's this both up and down and left and right motion of the water molecules that are causing a wave to look like this. All right. So we call a water wave. We call that a combination, a transverse and a longitudinal wave. Okay. I want you guys to answer this question. Think about it for a second. Read it. Think about it. Talk about it if you want to. Did you guys all read the question at least? Okay, so let's talk about A, moving your hand up and down more quickly. Does that make the wave travel fast? Yes or no? Talking about a string that's being held on both ends. No, this one isn't that, right? If we go back, we're thinking about this equation here. Okay? How about moving your hands more? Forget about distance. Forget about how fast you're doing it. We're doing it more. No. How about using a heavier string? Yeah. Using a lighter string. Would it increase the speed or decrease the speed if you increase the mass? Actually, let's go back. I don't know about C. I didn't think about it enough. If we went back to the equation, I'm just going to write it here. Velocity is equal to the tension force divided by mu, and mu is equal to mass over So if I increase the mass, I'm increasing the denominator, and therefore, what am I doing to my? So actually, yeah, my velocity is going down. So C wouldn't work either. The question's asking about increasing the velocity. How about D? Yeah, okay, so D one works. How about if you make it tighter, if you increase the tension? Yeah. And if you make it looser? Okay, we got it? A wave ball, a wave pulse travels along a string at a speed of 200 centimeters per second. What will the speed be if the string tension is doubled? Force of tension over the coefficient. I went dark. Why? So what would happen to the speed if the string tension is doubled? Square root of 2 is what? 1 point, whatever. It would increase or decrease, first of all? It would increase, right? And it would increase by a factor of square root of 2. Very good. So here, right? Let's write that down. Increase factor of the square root of 2. What if the mass is quadrupled, but its length is unchanged? So the mass is increased by 4 times. What would happen? By what? It would increase by the square root of 1 over 4 or decrease by the square root of 4. Same thing. Just a different way of saying it. So you're absolutely right. What's the square root of 4? So decrease by 2 times. The string length is quadrupled and its mass is unchanged. Increase by 2 times. Exactly. And the string mass and length are both quadrupled. No change. All right, you guys are good. Any questions on this? It's pretty straightforward. Um, can you answer this question for me? Who has a guess? What is the particle doing again? Up and down. If it's up and down, that means there's a point at which the velocity is what? Is what? 0. And then when is it the fastest? In the middle. And then it reaches the bottom. It's going what? 0. So the velocity is actually changing, right? What about the velocity down my wave? Is that a constant velocity? If I do this at a constant rate, constant frequency, my wave is traveling down at a constant velocity, right? So what would the answer to this be? No, they're not related at all. Okay? Does that make sense? We're going to talk about these two numbers here. We don't have time for this. Okay, that's it for today. Yeah. Do it once. It's the amount of time it takes from the wave, the energy, to reach the other end. That's your speed. In an ideal world, it will be constant. In a real world with friction and air resistance, it'll decrease. Yeah. All right, guys. See you Wednesday. Oh yeah, and I have my springs and rulers back.